Here we go.
With recording.
Just to introduce the video and say that today we haven't recorded as much as we usually do because we had some technical issues. They appear to be resolved now. So here at the end, we just want to,
It's one of those
as shown over
tasks,
here,
you
completely
can't
on the
see
video.
it.
So I will write it down continuously. But the task is to give a linear system of equations with two equations and two unknowns. Write down the coefficient matrix and calculate the determinant. So let's start by writing down the system of equations. So the task looks like this. The system of equations is called
3 to 1
minus 2x2 and minus x1 plus 3x2. Should I draw a line? Have I written it correctly? Yes. And the first question is, given you have such a linear equation system, did I write it wrong? Minus 3, yes. It should say minus 3 here. Thank you for that. Given such a linear equation system, what does the coefficient matrix look like? And it's a very basic question, just to show that you know what a coefficient matrix is. It's a rectangular numerical scheme. You write matrices with capital letters and two lines underneath. Then you input all the numbers in this rectangular scheme, specifically the numbers multiplied by the unknowns on the left side of the equal sign. So it's 3 and minus 2, and minus 1 and 3. And then it says you need to find the determinant of this matrix, and it's easy when it's a 2 by 2, because it's just this times this minus this times this. So the determinant, it gives us 3 times 3, which is 9, minus 1 times minus 2, but that equals plus 2, and 9 minus 2 is 7. And since 7 is not 0, so we can say something right away. The two equations here are linearly independent. This is a straight line, and this is another straight line. It is not the same straight line twice, and therefore we immediately know that if you graph it, we have a situation where two straight lines intersect at exactly one point. So we get precisely one solution. Then you need to answer whether matrix A is regular or singular. We can say that right away, since the determinant of our matrix is different from 0, and it was indeed 7, which is not 0, well, that means the same as saying that A is regular. Furthermore, it should be noted that you can only find the determinant of a square matrix. And it is square because there are an equal number of rows and columns. This is a 2 by 2 matrix. Then you need to solve the system of equations. And for this, we start with question C to solve the system of equations and write out our total matrix. And this is what we in English call an augmented matrix, where we have combined the coefficient matrix with the right-hand side. So it will look like this: 3, minus 2, minus 1, 3, and then we draw a dashed line to indicate that the right side follows, which is 5, minus 3. And if I were at an oral exam, I might say, please note that the augmented matrix is a 2 by 3 matrix. There is one extra column. So for a system of equations with two equations and two unknowns, the augmented matrix becomes a 2 by 3 matrix. And we usually write it like this. You need to specify the row number first, and then the column number, because someone decided it should be that way. It's a definition. So that's how it must be done. And then we proceed to perform Gauss-Jordan elimination on it. So what is the first thing we might do? We would like to have a 1 here, so we multiply row 1. We multiply row 1 by the number 1/3, and then there will be a 1 there and minus 2/3 there. And here are 5/3, like this. And here it still shows -1, 3 and -3. And now we really want what is over here to become our unit matrix, or identity matrix, as it is also called. So we want 1s on the diagonal and 0s outside. Therefore, we want that 0 there. And we can get it by taking row 2
and add row 1.
So if we do that, then we still have 1 minus 2/3 and 5/3, because in the outer row we haven't done anything. And here we have -1 plus 1, which is 0, and 3 minus 2/3, that's 9/3, minus 2/3, that must give 7/3. And here I get -3 plus 5/3, which is -15/3. So that gives -10/3 when I add 5/3. Do you agree? And then I would like a 1 here. So I multiply row 2 by the reciprocal of 7/3, which is 3/7, like that. And if we do that, we end up with 1 minus 2/3 and 5/3. And then we get 0 and 1. And when we multiply 7/3 by 3/3, the 7s cancel each other and the 3s cancel each other. And when I multiply here, the 3 cancels, giving -10/3. There we go. Do you agree? Did I miscalculate? Hey.
70 parts.
Maybe I miscalculated.
Is this where I made a calculation mistake?
Let's just try to see. That's when there are 9/3 there. And then I add 5/3. That's correct. Here it says 9 minus 9/3 plus 5/3 is -4/3. Is that correct now? And what did I do here? Then I multiplied through by 3. So 3 cancels out, giving me -8. Be patient for a moment. Now it's -4/3 times 3/7. Let's see. What have I got? -4/7 here.
Yes, so here you go.
-4. Part 7. When I multiply that fraction by that fraction, 3 cancels out with 3, and there's -4. 700 divided left. That must be correct. Like that. Then we want that 0 there. So we take row 1 and add it with 2/3 of row 2. Row 1 is added to 2/3 of row 2. And let's see what we get. Then we get 1 minus 2/3. No. We need to do it up here. So I say 1 plus 2/3 is 0. It's still 1. Then I say minus 2/3 plus 2/3 is 1. That gives 0. Then I say 5/3 plus 2/3 is -4/7. We must write that down. So we write right here 5/3
Plus 2/3.
multiply by -4/7. Does it look right? And what can we do that? -8. 21st fraction is written there like this. And this gives, if I extend by 7, then it gives 35, 21st part. Isn't that right? And then I can subtract 8 from 35, which gives 27. Do you agree with me on that? So here's where one should stand. 27th of January, 2021. And here it should still say 0, 1, -4. Part even. I hope you agree with me on that. So that means we have now found the solution. Up here is x1 and here is x2. So we can write the solution like this. (27, 21) part and minus. July 4th. And that was the solution. So it says the inverse matrix of A, if it exists. And the first thing we can say is that inverse exists. Since A is regular, A was a square matrix with a determinant different from the regular one.
And since it is regular, it has an inverse.
And we can find it. The inverse by taking the reciprocal of the determinant of our matrix and then multiply it by the adjugate. And she is there and usually writes it as adj.
Matrix A like that.
So that must give 1/7 because the determinant was 7. And then we need to work with the adjugate version of A. That means I need to swap the diagonal elements. It remains the same, 3 and 3, and then I have to change the sign. So here it will be 2, and here it will be 1 when I change the sign outside the diagonal. And then I can multiply in, so I get 3/7. 2/7 here, and 1/7 here, and 3/7 here. So that was the inverse.
There it is. Now observe.
The similar mapping that sends us from R2 to R2, which is given by, and I'd better just write it down. I think I'll erase a bit over here. We have a linear transformation, and that is question E. We have a small mapping that takes us from R2 into R2. Because we have two equations with two unknowns, and the determinant is different from 0, we know that we map from R2 into R2. And our function f takes the x vector as input by multiplying the mapping matrix with the input vector x, resulting in y. And then it specifically mentions the image of I and the image of j.
But it's very simple. We already know the image of,
What should g be? It should give 3 over -1 for the first column.
So that should give 3 over -1.
We could also have just looked to see what the first column in our mapping matrix is. Now I've erased it, but it was 3 -1. So that must be the image of I. And similarly, I can find the image of j. Keep looking here, -2 and 3. So that was the answer to that question. Then I need to look at the two columns in A that I had written down, and I will realize that they are the ones. And of course, this was to really emphasize that if you look at our coefficient matrix, which is also our transformation matrix, well, it looked like this: 3, -1, -2, and 3. So you can see that this coefficient matrix contains the image of I as the first column and the image of j as the second column. So that was what we discovered in question F.
So our brain thinks, aha.
That's how you create a transformation matrix. You simply figure out where the basis vectors are sent. In the end, you need to describe in words what F does to R2, and we can draw it to understand it. Because that linear transformation, what does it do to R2? So we can just draw R2 here, where we have the x1 axis and the x2 axis, and then we have basis vectors I,
and then we have basis vector j.
And if we allow ourselves to draw the output space over the input space, we know that Aurico is mapped onto Aurico, so Aurico doesn't move. And where is I sent? Well, it is sent to the vector 3 over -1. So 1, 2, 3, and then 1 down. So it goes like this and lands there. So we can see that the unit vector I is stretched and rotated simultaneously. So this is the image of I.
And where does it land? Well, it lands
The
on the
vector
scale.
-2 over 3. So I need to go 2 to the left and 3 up.
So it lands there. That's the image of j.
So it stretches and becomes longer while it turns over here, then it lands there. So if we describe in words what happened, areas will be scaled by a factor of 7, because there is an area that was originally 1, but these two vectors span a parallelogram.
Can I find a sign for
It should look like this. So this area here is 7 times larger than the small square that is there. So the transformation scales areas by a factor of 7.
This is the first. So the F scale.
Hey. A factor of 7.
Oh,
It's doing a shift. Can you see? It shifts like this, but it also shifts like this. So it's like a double shift, and F performs a double shift. For R2. So you could have flipped the entire problem around and said, imagine you want a linear transformation that does this with the two-dimensional space. So what should the transformation matrix look like? Like that. And then the rest follows. Then the system of equations, and so on comes after that. And that means you can actually decide what should happen in the plan. And then you can create a mitigation matrix that does exactly what you would like. Are there any questions about this? Okay, and now? Otherwise, I'd like to share a bit of what I planned for today instead of just solving a lot of problems. But I think it went well with working through many problems.
I want to tell you a little about linear
Independence. And I think we'll explore it by discovering it through some small examples. So it will only get mathematically heavy at the very end when I write up the conclusion. But all the discoveries are actually quite simple. So let's jump to board number 6. And then let's take a look at linear independence. How can one investigate if a given set of vectors is linearly independent?
Boom.
So that's our headline.
Linear independence.
I just think we'll play around to discover what I'm going to say. So imagine we're making this discovery. Something first. If I have a vector here, I call it vector A,
And a night watchman here, which I call the B vector.
and imagine that this point here is over in yesterday. Can I do something with vector A and B so that I end up at the origin? Yes, I can. If vector A is exactly as long as vector B, then I can just add them together.
That is the vector that will give magic.
They cancel each other out. You could think of it as forces. If one force is as many newtons strong as the length of this vector, and the other force is also that many newtons, then because they point in opposite directions, they cancel each other out. So simply by adding them together, you get the zero vector. So the game we're playing now in our exploration is forming the zero vector. Yes, we can. We can form the zero vector by adding vector A and vector B, which gives us the zero vector. That was my first example. Let's try to play a bit further with the same idea. What if the situation looks like this? Here is a vector. I call this vector A. And here is another vector.
There is twice the distance between you
I
and me.
call it vector B. And this is the origin.
Now it's gone.
Remember, the zero vector is the vector with coordinates 0 over 0, which corresponds to the origin. That was just up to a point.
Can we now form origo by combining our?
Yes, we can. We can simply take 2 times vector A and add it to vector B. Because if I take 2 times vector A, I get a vector twice as long, and it will be exactly as long as B, because B was twice as long as A. And when we add them together, we get the zero vector. So we could do that too. Are you following so far? Here comes the next example. Here lies the origin.
Here lies vector A. And here is vector A. B and B is exactly twice as long as A.
But aligned according to the manual, we can now create Auric by combining A and B. Yes, we can do that. We simply take vector B and then subtract 2 times vector A, for example. So that is vector B minus 2 times vector A. That gives vector 0, meaning the 0 vector. Are you with me on that? Because if I first say, go from the origin to B, and then take minus 2 times vector A, I end up at the origin. And by the way, notice what I've done in all 3 examples so far. This example, that example, and this example. I've created linear combinations of 2 vectors to form a 0 vector. And it was possible in all cases.
But now comes what I want to show you. What if the situation looks like this? Here's the driveway.
And I will handle this. And this is important.
Can we now make a linear combination of weights?
There's the B1 and G0 vector. What do we get if we just add the A vector and the B vector together? Then we get the vector that starts there
and ends out there.
And that is not the 0 vector. What could I do then? What if I took vector A and added it to negative vector B? No, that would give
yes,
this.
it's right here. It's not the 0 vector either. Can I even form the 0 vector by combining A and B?
So my question is this. Is there a number alpha that I can multiply vector A by and a number beta that I can multiply vector B by, such that when I add it all up, I end up with the 0 vector? Is that possible?
Is it possible then? Do you have a solution?
What should alpha be? What do you mean?
Both must be 0, and that is the only solution.
This is a very important discovery to understand what is coming up next. The only solution is that the 2 constants must both be 0. Yeah. Everything else will result in a vector that is not 0 in length.
And no matter how you combine samples A and B,
in a linear combination of them, it will yield a vector of 0 length unless we multiply both the A vector and B vector by 0.
So the only solution
is that alpha must be equal to beta, which must be equal to 0. So all those scalars must be 0. Otherwise, it cannot be done. So what is the difference between that example and that example and that example and that example? The difference is that in the first 3 examples, it was possible, but not the last one. And look, what is true for the 2 vectors? They are parallel. They are parallel to each other. What is it that's there for yours?
Vectors, they are parallel to each other. The 2 vectors are parallel to each other, but the 2 are not parallel.
When they are not parallel, we call them linearly independent. So here, vector A and vector B are linearly independent. It should have said are here.
Hello?
A and B resemble each other.
Are dependent.
And that's what it means. Simply put, that they are not parallel.
So we'll just put that in parentheses, right?
Not parallel. So if you have 2 vectors that are not parallel, the only way to make them result in the 0 vector by combining them is if the constants you multiply them by are both 0. Does all of this only apply in 2 dimensions then? No, it actually does not.
Let's try to come up with an example in 3 dimensions.
Imagine that here we have a room. And let's just say that the vector starting there and ending here is vector A, and the vector starting there and ending there is vector B, and the vector starting there and ending there is vector C. And this is where I ended my lesson yesterday. Is it possible to form the 0 vector, which is called 0, 0, 0, the 3-dimensional 0 vector? This one here. Is it possible to end up there?
By combining A, B, and C with constants.
Like this. Some constant times vector A, plus some constant beta times vector B, plus some constant gamma times vector C. Can it result in the 0 vector? Yes, it can, but it requires that alpha beta, and gamma are all 0. As soon as they are not, we will get a vector that is not 0 length. Can you see that?
So,
The only solution to this is that alpha equals beta equals gamma alpha equals beta equals gamma equals 0. And when that is the only solution, then they are linearly independent. So it is because they are linearly independent that this is the only solution. Imagine vector A, vector B, and vector C are all spanning the same straight line. Then it's quite easy to add them together and get the 0 vector by just multiplying with some appropriate constants. Can you picture it? And now comes what I wanted to write down, but didn't dare to until you had seen all the examples. Here is the sentence that's coming up now.
it sounds like a set of vectors, a set of vectors.
Vector foo1, vector v2, all the way up to
Vector Voigt.
so a set of k vectors where there should be as many as necessary, but there must be a finite number, for example 1000. A set of vectors is called linearly independent. Affection.
Legend is independent.
The bond equation equations, I'll write it up here. Lambda 1, which is just a number, it's a scalar, multiplied by vector v1, plus lambda 2 multiplied by vector v2, plus dot plus lambda k times vector vk equal to the 0 vector. And now that I am in so many dimensions, I actually need to underline my vector. So I must do that.
It is incredibly strange.
Oh well. If that equation only has one solution, where lambda 1
and lambda 2 and lambda 3 and all the lambdas
It's similar
are
to
0.
growing. So now I've backed
generalized,
up.
they would have discovered it. Und heck, the solution that lambda 1 is the same constant as lambda 2 is the same constant as lambda all the way to k. Let's just put some spaces in between here. Equal to 0. Are you following that? So even if you're in a space with 27 dimensions and you have 27 vectors, if these 27 vectors are linearly independent of each other, then you can only combine them to give the 0 vector if all the vectors are multiplied by 0. That's essentially the point. And that means you can examine such an equation to see if a given set of vectors are linearly independent from each other or not. And the way you can do it in practice is by writing your vectors as columns. In a matrix, you perform Gauss-Jordan elimination on it, and then you count the number of leading ones. And if you get as many leading ones as you have columns, then it's linearly independent. If you get one less, then it's linearly dependent. Two less, also linearly dependent. At least one of the vectors can be expressed as a linear combination of the others. And that was essentially what I wanted to tell you today, along with some examples. We haven't gotten much further, so we'll have to continue next time. But the point is, and that's what's important, if you are in a three-dimensional space, how many vectors are needed to span it? 3 linearly independent vectors. Because if you had fewer than 3, you couldn't span the space. And if you have more than 3, they are not linearly independent. Is it possible to have 3 linearly independent vectors in the plane? If it is one and it is the other, then you can form it using those two. So it is not possible to have 3 linearly independent vectors in the plane, you can have a maximum of 2, but it also requires at least 2. And describe the plane. Therefore, it requires exactly 2. Are you with me on that? So to span the plane, it needs exactly 2 linearly independent vectors, because more than 2 cannot be linearly independent, and fewer than 2 cannot span it. And the same can be said about any space, no matter how many dimensions there are. The 27-dimensional space requires exactly 27 linearly independent vectors, because fewer than 27 vectors cannot span it, and more than that cannot be linearly independent. And that was the message I wanted to share with you. Thank you for today, and have a nice weekend.